Right now, artificial intelligence in software systems acts as a strictly passive entity. It is a highly capable, yet stateless tool waiting for a prompt. When engineers try to scale these models across millions of lines of enterprise code, this reliance on text prompts creates a massive bottleneck. Developers have to manually extract repository logs, paste in architectural context, and constantly supervise the model's output just to execute a single isolated decision. The friction of spoon-feeding Ada chokes real-time operations. Scaling this technology requires dismantling the chat window entirely. We have to integrate AI not as an isolated service, but as an autonomous architectural component that navigates the environment on its own. This taxonomy explicitly separates true autonomous agents from chatbots. Under planning and decomposition, the first trait is goal orientation, autonomously breaking high-level objectives into actionable steps. Finally, under state and memory management, we find situational awareness. Agents maintain persistent state across tasks. When you synthesize these traits with the ability to actively execute external tools, the AI adapts its workflow dynamically. It transitions from a tool you wield into a participant on the team. To see this applied, we can look at a multi-agent ecosystem designed for high-velocity enterprise software, known as the Software Quality Companion. The entire autonomous ecosystem wakes up the moment a human engineer opens a pull request to submit new code. This flow diagram maps the operational lifecycle that takes over, replacing simple text generation with a 6-layer agentic stack. Focusing on the top tiers, the perception layer ingests raw environmental signals, while the memory layer retrieves historical coding conventions, past decisions, and architectural constraints. By maintaining this historical project context, the system avoids evaluating new code in a vacuum. It cross-references the submission against the long-term structural reality of the organization. Evaluating a massive enterprise codebase is too demanding for a single AI model to handle accurately. The workload must be split among specialized expert subagents. First, a code review agent strictly scans the incoming files for syntax flaws, local security vulnerabilities, and potential performance drops. At the same time, a test generation agent analyzes the exact same code to identify coverage gaps, synthesizing new test vectors for unproven logic branches. Finally, an architectural consistency agent monitors the big picture, scanning for system boundary violations. But specialized agents often disagree. The code reviewer might suggest streamlining a database query for pure speed, while the architectural agent realizes that modification breaks a strict microservice boundary rule. To prevent a deadlock, a central orchestrator agent steps in. Instead of relying on loose heuristic prompting, it applies a deterministic priority matrix to evaluate the conflicting directives. Because domain boundary compliance ranks higher in the matrix than local query optimization, the orchestrator automatically overrides the code reviewer's tweak. It synthesizes a revised recommendation that satisfies both constraints. By handling task decomposition, conflict resolution, and tool execution internally, this multi-agent structure eliminates the need for human micromanagement. Granting an AI network the autonomy to alter external software states introduces severe operational risks. Without proper boundaries, controllability failures occur. Poorly constrained agents can enter high-cost recursive runtime loops and rapidly consume server resources. There is also objective misalignment, where an agent might optimize a proxy metric, like maximizing review speed, while quietly bypassing organizational security rules. Expanding an agent's permissions to use external tools broadens the attack surface, creating direct vectors for prompt injection or proprietary data exfiltration. Agent safety cannot be patched with better prompt engineering. It must be hard-coded as an immutable architectural property that physically stops catastrophic action. Looking back at the architectural stack, this safety is enforced by the bottom tier, the governance layer. By default, agents operate under a principle of least privilege. They have read-only access to repositories and possess zero implicit authority to write to production environments. Before any state-changing operation or destructive modification can happen, the system triggers an action gate. Everything pauses, demanding explicit, human-in-the-loop approval. For the human engineer, the daily workflow completely changes. They receive a synthesized, evidence-backed report, review the logic, and simply click Approve, entirely insulated from the friction of prompt engineering. The future of software engineering lies in this ecosystem. Autonomous AI teammates execute the complex logic within rigid, safe boundaries, allowing human engineers to step back and operate as strategic decision makers.